All right, we're going to get started, in part because last year we had so many great questions, and we want to make sure to have a chance to address them all. So I'm Susan Domchek. I'm the director at the Bassler Center for BRCA, and I'd like to welcome everyone for attending this third annual Breakthrough in Discoveries panel. We have this great panel of national and international experts, and we're going to give you a lot of information. One change is that Judy Garber was not able to make it tonight, so Mark Robson, you want to put your hand up, Mark, who does not have a card in front of him, but Mark Robson, who's from Memorial Sloan Kettering, is subbing today. I'll introduce everyone in a moment. So as an oncologist, I have the honor of treating patients affected with hereditary cancer. I also have the unique privilege in being the director of the Bassler Center of collaborating with researchers within Penn and also throughout the world at different cancer research institutes. And I think that the important thing is that there's this unprecedented collaborative efforts that are underway, and this is really made possible due to a lot of different resources. For me here at Penn, being part of a large university, and because of great leadership from our Cancer Center Director, Chi Dang, our Dean, Dr. Larry Jameson, our Healthcare CEO, Dr. Rolf Mueller, and our Chief Scientific Officer, John Epstein, many of whom are here today, have really helped make this all happen. But we're really here today because of Penn alumni Mindy and John Gray, whose visionary gift in 2012 established the Bassler Center in honor of the memory of Mindy's sister, Faith Bassler, who died of BRCA-related ovarian cancer. And now, on the center's 5th anniversary, for those who have not heard this, there has been yet another transformative $21 million gift that was just announced today, which is just remarkable. Yeah. That means that the total commitment is $55 million, and this extraordinary support ensures that we can be on the leading edge of research for generations to come. But more importantly, it really provides hope to many of us that things will substantially change. And just to put this in perspective, as Steven Narod just mentioned, 20 years ago, we didn't really know what BRCA1 and 2 did. We weren't using breast MRIs for early detection. We only had a rudimentary understanding of cancer risks. And we really didn't have much evidence to guide our management. We know so much more now, including how the genes functions. We have advanced screening techniques. We know much about preventative surgeries. And we actually now have not one, not two, but 3 FDA-approved therapies for advanced ovarian cancer, largely developed because of the information about BRCA1 and 2. So it's really an incredible state of affairs. But we know that we have a lot more work to do, so I promise you that we're not resting on those successes. In addition to those who are in the room today, and by the way, there's lots of seats up front, don't be shy. The dean's here, but he'll be nice to you. And we are also streaming the event on Facebook Live. So to those of you who are doing that, we welcome you. This year, too, we have note cards that are in place. So please write your questions down the note card. We'll have staff picking them up. We're going to try to answer as many questions as we can, including from our Facebook viewers. So before we get started, I'm honored to invite up to the podium Mindy and John Gray, founders of the Bassler Center.
Thank you, Susan. Thank you to our esteemed panelists here today who are going to help us translate the science into lay terminology and give us a chance to ask the questions that keep us up late at night. 10 years ago, Apple released its first iPhone, and I don't know about all of you, but I can't remember life before my Apple device. Or should I say, I can't remember time before I was inextricably tethered to my Apple device. And I feel the same way about the Bassler Center. This mission is our passion. And the Bassler Center clinicians, researchers, counselors, and support staff are our tether to hope. We are honored and filled with pride to see what they've made possible in 5 short years. As Susan said, 20 years ago, scientists had little understanding of what BRCA even did. 5 years in at Bassler, and we are exploring exciting new lines of treatment and promising new possibilities in detection. We established the Bassler Center in memory of my sister Faith, who died far too young from BRCA-related ovarian cancer. We dreamed of a place that would be a global hub for BRCA treatment, research, counseling, and care. It is days like today as world leaders in the field come together to share breakthroughs and discoveries that we know our dream has been realized. Thank you for devoting your life's work to this cause. Our families thank you. The families of those newly diagnosed and living in fear thank you. The families who have suffered the devastating loss of a sister, a brother, a mother, a son, thank you. We are forever grateful for your passion and your dedication to this cause. I lost my mother. I lost my mother, Pearl Basser, last month. Nothing made her prouder than seeing her name attached to a center with such an essential, such a life-saving, such a noble mission. So an additional and very special thank you for being here to honor her memory. We are more committed than ever to Basser, more committed than ever to the heroic work you are doing, which is bringing us closer to a cure.
As I said in the earlier session, Mindy's right, Pearl loved the Basser Center for lots of reasons. She particularly loved Susan, and it is very nice to be together with everybody here in her honor. When you walk into the Abramson Cancer Center, you may not notice, but as you go up the escalator, there are this funny white sculpture. It looks like some squids in sort of a circular thing, and you may wonder what that is. It is a symbol of what happens when broken DNA is getting repaired. And unfortunately, in folks with a BRCA mutation, that repair mechanism can break down. But it's there to give us a symbol of the way things should work, and it's called homologous hope. And really, that's what the Basser Center is all about. It's about providing hope to families that are affected by BRCA mutations. And that's what we want to do. And what we're obviously trying to do, of course, is encourage collaboration amongst the leading scientists in the world in this area and accelerate scientific discovery. As you're going to hear today, there's real progress. When we started 5 years ago, we had a sense that things were coming together at the time. I think today we feel like that is actually happening in a meaningful way. You'll hear about things like Parp Inhibitors, drugs that are specifically targeted to patients who have BRCA mutations and ovarian cancer. Hopefully they'll be able to get it for patients with breast cancer as well. We're also seeing signs, hearing signs of potentially that ovarian cancer starts in the fallopian tubes, which could have powerful impact on how we do prophylactic surgeries on women, and really things that are out there around potential vaccines, around things coming together between genomics and immune therapy, obviously in very early stages. But we feel very positive about the progress being made, and that's the reason why Mindy and I decided to make this additional gift. We have great confidence in Penn and Susan, the leadership at Penn with Larry and Ralph, Amy Gutman, Chi Dang. It's been extraordinary, the support we've gotten in building this Basser Center, and we couldn't be more pleased with where we're going forward. The one thing I'd say to the folks either here or listening in is obviously we're committed to this. We'd love to get your support as well. We've got our Basser Gene Bash coming up in November. Obviously, we'd love financial support, but there are other things around awareness. You can get involved. You can reach out to the folks connected here at the Basser Center. The more people, the more resources, the better our chances are. We encourage everybody to get involved. I'd say this afternoon we're honored. We have a wonderful panel here. You'll hear about each of them, but this is a world-class group of scientists, and it reflects well, I think, on the future for all of us in terms of what's to come. As Mindy said, we just want to say thank you to all of them. Thank you to Susan and the team at Basser. We are totally committed to what I think is going to happen over the next few years, and we really encourage everybody to join in with us in this fight. So thank you all so much.
All right, so this is going to be fun, and I'm going to do some introductions now. So starting on the far right, we have Dr. Steven Narod. He is this year's Global Prize winner for the Basser Center. And Steven, there's little about BRCA 1 and 2 that Steven hasn't been involved with over the years, from discovery to figuring out ways to prevent cancers. And because he's from Toronto, he serves as our international panelist. You could speak French for us if you'd like, and then I think think you lived in Quebec at one point, did you not? Right next to Steven is Dr. Roger Greenberg, officially professor at the University of Pennsylvania as of today. Congratulations, Roger. And he's the director of basic science here at the Bassler Center. Dr. Lewis Cantley is a cancer center director at Well Canal Cancer Center, and has done a great deal of work on a PI3 kinase pathway and the potential therapeutic implications that might have for treating triple-negative breast cancer as well as BRCA1-related cancer. And Dr. Mark Robson, who's at the Memorial Sloan Kettering Cancer Center, has been my collaborator for many years and has had an interest in therapeutics related to BRCA1 and 2 related cancers, as well as the clinical applicability of this type of information. So with those very basic introductions, we're going to get started. And Dr. Narod, first one to you. Can you tell us some of the key things we've learned since BRCA1 and 2 were first discovered in 1994 and 1995?
Well, there's scientific things about the function of the gene, which I'll defer to Roger on in terms of basic science, but I think what's interesting what we learned is these are the big two genes. I mean, 1994, 1995, that was sort of the tip of the iceberg. Turned out to be the iceberg. There's been 29 other genes found. If you put all those other 29 genes together and add them up, it doesn't come to BRCA1 and BRCA2. So what we've learned is that's the big story. It's those two. And we're 100% sure we should test for those. There's still discussion about the other 29 or the other 200. A second thing I think we've learned is if you can deal with the breast cancer and the ovarian cancer, you pretty well beat these things. There are a whole lot of other cancers out there, a lot of discussion, whether it's endometrial cancer. We know there's a prostate cancer. We know there's a melanoma. We know there's a pancreatic cancer. I try not to overwhelm my patients or my collaborators or other scientists with the idea that this is an immense Pandora's box full of cancers, full of, tribulations, rather that if we can focus on breast cancer and ovarian cancer, we will reduce the majority of the grief. The same way, putting it this way, and I think it's a tremendous accomplishment, although we're still stuck with the surgeries. If I could take a 35 or a 40-year-old woman who has a mutation and she goes through the full range of preventive surgeries, not perfect, but her life expectancy is now pretty much that of an average woman. And I mean, so the idea being, should we be doing, prenatal diagnosis? Well, you could. I mean, I'm not going to say yes or no. We generally don't do it. But the idea that we can, with known knowledge, with surgeries, I mean, a lot of the reconstruction that we now have in breast cancer by our plastic surgical colleagues is so good that it really reduces the burden and the impact psychologically of the preventive surgery. And I think we feel that we can be pretty comfortable about giving HRT and reducing the burden of premature menopause. It's a long answer, but I'd say in terms of life expectancy, we're pretty well there. We should still focus on the big issues. We shouldn't start thinking too much about, I want the basic scientists to tell us what to do to find the right pill. Don't get me wrong. But as clinicians, I think we get a tremendous amount of benefit through implementing what we already know.
Great, that's great. And it's a great segue. Roger, tell us more about what we've learned about the function of these genes.
We've learned a lot about the function of the genes over the past 20 years, and I think with new technologies that's going to explode even more. In 1996 and 1997, the first clues to how these proteins work came from David Livingston and colleagues, actually our previous Bassler Global Prize awardee, in which they showed that they localized the DNA damage sites and they're involved in homologous recombination. Parp inhibitors emanated from that years later. Now we're starting to understand resistance mechanisms and so forth. What we've really learned to a great extent is how these proteins function in the DNA damage response and these other 29 genes that Dr. Narod mentioned, many of them came because they interact with BRCA1 or 2. So that's provided a wealth of data, and it has led to the development of Parp inhibitors, to the basic understanding of how these patients respond better to platinum. And it has led to emerging concepts of resistance. And there are now new sort of targets that could, in principle, be targeted in the resistant cells. One of the biggest issues that we're still dealing with is tumor heterogeneity. Within a tumor, not every cell is the same. And that leads to the unfortunate lottery of resistance. I think overcoming this tumor heterogeneity on a cell autonomous level by targeting the compensatory DNA repair pathways that take over in the resistant cells is one way of doing this. And the other ways in which we've, I think, heard about a little bit about today is sort of activating other responses, such as the immune system or cytokine responses, other responses that can be delivered in a more systemic manner. And that is a new and emerging area. And there's a lot more biology that we have to learn about these cancers simply beyond their defects in DNA repair. And I think that's an exciting area for future development.
So that's great, Roger, and there's a lot in that. So I'm going to take it down a little bit. And Mark, why don't you tell us a little bit more about Parp inhibitors and what we've learned so far about these agents?
Okay, so Parp inhibitors, Parp is a protein. It's actually a family of proteins, and they're called poly-ADP ribose polymerases, which is why we say Parp, because you can't get that out 3 times fast. And it turns out that it's involved, or the major members of that family are involved in a different DNA damage repair pathway than BRCA1 and BRCA2. And that if you inhibit that pathway, which can be done with a series of oral compounds, now pills, what winds up happening is Parp doesn't do its job. The DNA damage that usually gets fixed by Parp doesn't get fixed. And where in normal cells, BRCA1 or BRCA2 can step in to essentially take over, in the cancer cells in a BRCA carrier, which don't have BRCA1 and BRCA2, that doesn't happen, and the cell winds up dying. At least that's the canonical explanation. There's probably some other explanations as well, such as a physical barrier to DNA replication and the like. So these drugs were shown first in test tubes and in vitro experiments to be pretty effective in killing cells that didn't have BRCA1 or BRCA2, and over the years, they have been rolling into clinical trials. There are approvals, as Susan said, for ovarian cancer in both the United States and Europe. There has been a trial which we'll be reporting at ASCO, which shows benefit in patients with BRCA-associated breast cancer. And there's very active exploration going on with FDA breakthrough designation in prostate, and there's interest in pancreas. So it's really one of those unusual circumstances that hopefully will become more common, where science has led to an intervention which has led to a clinical outcome and a beneficial intervention for patients. And really excited about continuing to leverage that moving forward.
And it is just such an exciting area, and one that I'm not sure that we all could have imagined 10 years ago. So Lou, tell us a little bit about the PI3 kinase and how it might or may not relate to Parp inhibitors in therapy.
Yeah, so PI3K, like Parp, is an abbreviation for phosphoinositide 3 kinase. My laboratory discovered this enzyme at the end of the 1980s, and it turns out to mediate everything that insulin in your body does. And so when you have insulin resistance, it's because you can't activate PI3K in your muscle and liver. But we discovered it because of its co-purification with oncoproteins, proteins that cause cancer. And so we had this very curious dilemma that the same enzyme that mediates everything insulin does, when overactivated, causes cancer. And that got us thinking about the concern that having high insulin in your bloodstream may actually be driving some cancers. And in fact, we know that people who have insulin resistance are at much higher rate for cancer than those who don't. And so that has suggested to us that if we can keep insulin levels lower, we may reduce the risks of a whole variety of cancers. The ones that have the highest risk, in fact, turn out to be many of the women's cancers, particularly endometrial, breast, ovarian, pancreatic cancers at much higher risk. And we now have evidence that those, in fact, are driven, those cancers, in fact, are to some extent driven by insulin. They have insulin receptor on the cancer, so if your serum insulin goes up, as it does when you have insulin resistance, your muscle and liver don't respond, but the cancer still does, and so it takes up the glucose and grows instead of your other tissues. So that's the area where we're really focusing on resistance, on prevention, but also we realize that if you can block that insulin-dependent stimulation of an existing tumor, you might be able to treat it more effectively with drugs. So PI3 kinase inhibitors are in clinical trials, have been approved for CLL, and are in clinical trials for particularly for breast cancers, triple negative, in combination with olaparib, the Parp inhibitor, based on work that our Stand Up to Cancer team did. And so we're trying to understand how better to use these drugs, and in particular, how to keep insulin levels low, which we can do with diet. So the dietary intervention is far safer. In fact, believe me, you could not have another bite of sugar the rest of your life, and you would not have any dire consequences other than perhaps depression. And that will only exist for about 6 weeks, and then you'll get off the addiction. You don't care anymore. Believe me, I haven't had sugar in years.
You are a better man than I am, having been addicted to chocolate. So we're going to stay on therapy for just a minute, and then we'll move back into prevention. So Roger, the next one's for you. Tell us a little bit about the ways that PARP, that tumors can become resistant to PARP, and I'll particularly nudge you in the direction. Talk about reversion mutations for a minute, because they're weird and cool.
So,
Use the
people use
microphone.
You hear me? All right. So there are a number of ways in which tumors can become resistant to PARP inhibitors. If we think about BRCA loss, it is both predisposes to cancer, but also creates Achilles heel by treating with agents that cause DNA damage, and now the tumors have lost both BRCA alleles, both BRCA genes, and cannot repair the damage, and thus they become hypersensitive to these agents such as PARP inhibitors or platinum. One of the bona fide mechanisms of resistance in cells that are cultured in the laboratory and in patients is something called a reversion mutation. And that is, if you have the length of the sort of BRCA gene right here, and there's a mutation that disrupts its function right here, a way around it in which it can revert is to create breaks on either side and rejoin and ligate and to create a functional protein still. And this is a resistance mechanism. So the tumor was originally defective in BRCA function, and it has a secondary change that now allows it to have normal BRCA function. And that's actually not a good thing in the context of therapy, because now the tumor has competent DNA repair capacity and is no longer hypersensitive to these inhibitors, such as PARP inhibitors, or these drug agents such as PARP inhibitors or platinum. That's one mechanism. There are other mechanisms that can achieve the same thing by what we call rewiring of DNA repair capacity. Other changes within the whole broad network of DNA repair and other genes, loss of them can actually also restore what we call homologous recombination type of DNA repair in these cancers and allow them to become resistant to these agents as well. And so it is a constant battle in the laboratory between understanding these and how to stay one step ahead of the tumor.
And so we're hopeful that types of combinations, including PARP inhibitors and PI3 kinase inhibitors or other things, might prevent that type of resistance from developing in the first place.
Exactly. And in fact, we even heard one of the talks today talking about Pol theta, and that's an additional interaction that is also known to be synthetic lethal with BRCA. And so the hope is that if a tumor does become resistant, there will be agents that will attack Pol theta or other targets within the cell that will restore sensitivity.
So great. So now we're going to move into prevention. And before we get into denosumab, Mark, I'm going to ask you, why can't we use PARP inhibitors for prevention?
Well, I mean, one day we may be able to. I think one of the concerns, which is purely at this point a theoretical concern, unless you're running the FDA, is that there do appear to be increases in certain forms of DNA damage in, for instance, the bone marrow of people who are, or animals that are getting PARP inhibitors. And the corollary or the downstream concern of that is that could that then potentially increase the risk for things like hematologic malignancies? That is completely theoretical, but the job of the regulatory authorities is to worry about theoretical things in people who are healthy, such as those who are unaffected. So there's, in a sense, a different bar for safety in thinking about exposing essentially normal individuals to an agent compared to using a cancer therapeutic. There may be biologic reasons why it may be a challenging strategy. I mean, Dr. Cantley's stuff today wasn't that encouraging, I mean, in terms of olaparib as a prevention agent. But that, I think, is the fundamental reason why the prevention trials have been hard to get off the ground.
Now, there is a very large, what we call adjuvant study, so for women who have breast cancer and have been treated for cure, and in that study, half the women are getting olaparib and half are getting a sugar pill, and we'll be able to see the toxicity. So we are working on these things actively. Lou, I don't know if you wanted to comment at all about PARP inhibitors for prevention, then we're moving to denosumab with Steven, so.
Yeah, I completely agree. I think that is the concern, and as we have more and more patients on olaparib as an approved drug for ovarian cancer, we will be able to hopefully do observational trials on those patients. More than observational, because we'll have to do bone marrow, probably biopsies, or at least follow blood in those patients to see whether there are hematological disorders showing up at early stages, which can be monitored by very carefully with existing technologies.
So now we're going to move to, well, Steven, you can comment on that, but also I'd love to hear about, other ways to do prevention. And specifically, you were talking about denosumab today, and I think this audience would love to hear more about what that is and what it could mean.
Okay, but I mean, with regard to that question and this question, I think, Mark and Lou made interesting remarks, important ones, about using something like a PARP inhibitor for prevention. A question that I raise or try to answer, and don't do either, well, is how do you know it works? The trouble with knowing it works is the trouble with prevention for breast cancer in general, because what do you measure? I mean, ideally, the only thing we can really measure in a prevention trial of breast cancer that I'm going to be willing to tell a patient this is going to work. First of all, I don't tell the patient, you should take this because it'll work. I tell the patient this is a viable alternative to preventive surgery. Otherwise, you're limiting your recommendations to people who say, I'm never going to have preventive surgery. And then you say, okay, well, as long as you're sure you're not going to have preventive surgery, try this. But I want to have a drug that's an alternative that I can rationally recommend. So I got to have a drug that works real well, because preventive surgery works real well. So it has to be in the ballpark. I mean, we can go from 80% cancer risk to 2% cancer risk with a mastectomy. Now, is it ever going to be the case where I can give you a drug that drops it from 80% to 2%? Never. I'll settle for 8%. I mean, I'm settling, I'm a man without the situation, but I'm being theoretical. In other words, maybe the goal shouldn't be to get to 0 or 2, but to get to the same risk of a woman without a mutation, which is like 8%. But it's still a huge challenge. So if I got to go to 80% to 8%, I don't have something I can measure in the blood and say this is going to work. I can't take a blood sample or give a drug and say, your estrogen went down. This is going to work. Oh, your progesterone went down, your vitamin D or whatever. Maybe there are other diseases where that works. I can do that for cholesterol. I don't have to wait to get a heart attack. Your cholesterol went down. I don't have to wait to get a stroke. Your blood pressure went down. But for breast cancer, for 40 years, we've been stuck looking for the elusive biomarker of hope. And what we have is Ki-67 measures of proliferation. And they're just not good enough. There's no biomarker of breast cancer risk, whether it's mammographic density or estrogen level or Ki-67 proliferation indices of normal cells in the breast, that will ever get us to the point where I can say to the woman, take this pill, that'll work. I gotta measure breast cancer. Ideally, I'd measure mortality, but give me breast cancer. And that is a big study. Any study that will be designed to take healthy women and give them a drug versus a placebo and show a significant drop in the number of breast cancers, even in BRCA carriers where the risk is about 1.5% a year, will take 1,000 women 10 years. Can be done, but you better choose them bloody carefully because you're not going to get 3 or 4 chances. We picked denosumab. We picked it because of a lot of basic science, a lot of people on board. There's a drug which works. What do we like about the drug? It's a shot, you get it once every 6 months, right? It's good, compliance. So there's a lot of reasons. Maybe there would be, in the general population, you can have an option. One person takes this, one person takes that. We've tested aromatase inhibitors. We've tested vitamin D, I think. We've tested tamoxifen. But in this population, we have to collaborate. It would be nice if I didn't, but I mean, we have to collaborate in order to get enough patients to get a center together where we can get a trial. And it is a critical thing because we will not have 10 shots at this.
No.
So we better pick the right one, we better get the right partners, and we better get an agreement, and we need it. So it is a tremendous hope, but it is also something that requires some thought and a collegial spirit.
Well said. So Mark, in following up with that, tell us a little bit more about denosumab and what we know already in osteoporosis and breast cancer, just to give a little context about that this is a medication we already know.
Right, it's a medication we know very well. I mean, so it's approved. There's a formulation called Prolia, at least that's what it's called in the U.S., which is approved for osteoporosis, and it's the every 6-month injection that women without cancer, postmenopausal women in the general population can get. In the cancer space, for people who have bone metastases, there's a formulation called Xgeva, which is twice the dose and given monthly, which reduces the risk of bone progression and fractures. It has the same type of bone effects as the bisphosphonates, so like Fosamax, but through a different mechanism, and so it has a different side effect profile. It looks like they're pretty safe and very well tolerated in the cancer space. So apart from the fact that they are ridiculously expensive because they're monoclonal antibodies, it's a good agent, and I agree with Steven. I mean, it's relatively ideal for a number of different reasons, especially at a Q6-month dose. So, if it pans out, it's really going to be a pretty exciting alternative.
Right, and just to put it in context, tamoxifen and raloxifene are both drugs that are approved for prevention in the United States. Tamoxifen, it was a 22,000 woman study the tamoxifen versus raloxifene was 22,000 women. Tamoxifen was 13,000 women to get these answers. Now, these were not BRCA 1 and 2 carriers, and we did all that work, and hardly anyone takes them for prevention because the side effect profile is not favorable. So we need to be very thoughtful about what's the endpoint here. The endpoint is to get people to take medications. So we, as Steven said, need to be thoughtful about which drugs we choose to pursue. So we're going to change gears yet again, and Lou and Roger, I'm going to ask you, we don't know, the greater public doesn't really always understand basic science and how important it is. Can you guys just sort of comment on that aspect and how you go from the basic science into the clinician and what it means?
You want to start? Sure, and I think a great example of this is in the basic science of what led to the approval of Parp inhibitors. Parp inhibitors were originally looked at as radiosensitizing agents and were developed initially from basic science studies. BRCA in parallel was first implicated in homologous recombination. The landmark studies in 2005 in which the combination of PARP inhibitors and a BRCA mutant mouse embryonic stem cells that were either null, meaning 2 mutations in BRCA1 or 2, or 1 mutation in BRCA1 or 2, showed a 100-fold difference in 100-fold or more sensitivity into the null state, which mimics the tumor, versus the state when there's only 1 mutation that mimics the situation in every other cell in the body of a BRCA carrier. All right, only 4 years later, proof of concept in 2009 showed that these agents worked in cancers in which patients had BRCA mutations. This is one example, and there are many others. Much of what we know from basic science has come from even studying yeast, fruit flies, worms, mice, and so forth. And this sort of combination and this basic knowledge that has accrued over the years is now being applied in clinically useful ways. There is much, much more to learn, and basic science has a tremendous role in our understanding of these cancers and beyond that, often in unpredictable ways.
So since we haven't talked much about immune therapy, and it may be rightfully so because it's yet to have an impact in this particular disease, I think everybody realizes that immune therapy has suddenly been a revolution in melanoma and now lung cancer, a subset of breast cancers responding, a subset of colorectal cancers responding. So the basic science that led to this modern immune therapy, because people have been talking about immune therapy for cancer since the 1970s when antibodies, monoclonal antibodies were first discovered. We have made some understandings. It was really about 20 years ago that these checkpoints, the so-called checkpoints that create a balance between the subset of T cells that cause attack of tissues and the subset of T cells that hold them back. These are important because you would get autoimmune disease all the time. People who get autoimmune disease have this imbalance between the cells that attack and the ones that protect. In the tumors, what we're learning is that tumors have figured out, they evolve to use this to their advantage. So they can tell the adaptive immune system that wants to attack the tumor, stay away. I'm just normal tissue. Believe me, I'm just, look over there. I'm not the one you should attack. And so, quite honestly, most of us who were doing targeted therapy were completely ignoring these people because every therapy required about $2 million per patient to build something to specifically attack that patient's tumor. But now we realize we can get monoclonal antibodies that will work for a wide spectrum of people. Everybody just gets an injection every 2 or 3 weeks, and with miraculous responses. The question is, why do some respond and others don't? Part of it's because it's a total mutational burden. Melanomas get lots of your skin gets lots of sun exposure, lots of mutations. There's plenty of things for the T cell to see there that's different from a normal cell. Same thing with lung. Everything you breathe in is causing mutations, easy to detect, but not in ovarian and not in breast. Mutational rates are typically much lower. Yet we're beginning to see some responses to these checkpoint inhibitors where the mutational burden is extremely low. So what's going on there? Are there other things happening? Can we generate vaccines that will anticipate a state that the tumor is going to go through, that the immune system will recognize and be able to attack? The innate immune system, there are cells that normally are there to attack an infected cell that's, that looks slightly different, and you come in with neutrophils or macrophages and attack those. I think there are ways to turn those cells from protecting your tumor to actually killing the tumor. And so there's a lot to be learned here from the basic science of immunology. And those of us who were trained in targeted therapy are going to have to be totally re-educated by immunologists, such as Bob von der Heijden here, and others who have worked on this all their career. But I think there are tremendous opportunities and potentially for vaccines that could really block these tumors are ever evolving if we know the course of their evolution. And that's the trick, is to figure out the course of the evolution and what's the vulnerable point where you can reverse either the innate immune system or the adaptive immune system to attack that tumor. So it's still pie in the sky, but there's a logical approach to take to figure it out.
A cancer immunologist that I know once told me that cancer immunology was a 20-year overnight success, that for 20 or 30 years people plodded away, only all of a sudden to find that all their work actually had direct human application. So it's just a reminder about how important it is, the basic science. Mark, I think you had a comment.
Yeah, I come at this as a guy who failed PCR. I actually literally got thrown out of the lab because I couldn't do it. Honestly, I did. I was useless. They told me to go home and take care of patients. But I feel very passionately about this, and which I don't feel passionately about many things. And this is one of those things that is sort of a little bit under attack right now. There is nothing in modern medicine, surgery aside, that we are now dealing with that hasn't started as somebody's basic science investigation. And the vast majority of funding for basic science investigations comes from the NIH. I mean, philanthropy efforts are enormously appreciated, necessary, they're critical, they help with a lot of initial stuff and getting things moving, but the NIH is the source of most of what we are benefiting from today. And, focusing on maintaining basic science funding in the United States is critical. Otherwise, we're going to not have the innovations 20 years from now that we're benefiting from today. So off the soapbox, but please.
We got it, yeah. So that's going to be a great transition for questions. We learned last year that the number one thing people wanted was time for questions. And so I'm going to get these started. All right. Yes, these are all great questions. So I'm going to start from this one, which is Facebook, and this is really important. So I'm going to send this to Mark. What if someone doesn't live in a city with a big cancer center? How do they access clinical trials? How do they access genetic counseling?
Wow. So clinical trials they're kind of two different questions. I mean, clinical trial access for instance, therapeutic clinical trials, people are working very hard on efforts like, for instance, TAPER, which is a study that ASCO is coordinating, which is trying to get access to folks who are not part of conventional infrastructures. Most people probably have something that is within targeting distance. It's always interesting talking to Fergus how long people will drive to go to the Mayo Clinic for an appropriate trial, and it's hours. So going to clinicaltrials.gov, asking your physician to go to clinicaltrials.gov and identifying something is at least a way to start. The genetic counseling piece is a challenge that people are trying to meet through various alternative delivery models. There is active efforts to deliver telegenetics, telehealth type of applications to provide it, and these are coming from both academic enterprises and commercial enterprises. And so one way to just start is by going to the National Society of Genetic Counselors website, and there's a Find a Counselor button there. And you type in your zip code, find a genetic counselor who's in the general vicinity, and call them up and start talking about what your options and alternatives are.
I have an amazing number of terrific questions, so we're going to try to go through them quickly. What difference, if any, is there between treatment of germline and somatic BRCA mutations? I'm going to take this one quickly and say that in the past, we had no idea, and now we have data from several studies, including Ariel 2 and others, that suggest that it's actually the efficacy of these Parp inhibitors seems to be pretty consistent between somatic and germline. I don't know if we all expected that necessarily, but it looks to be true. We certainly need larger numbers and more information. Any comments on that from the group? All right, so the next question, which I think is, I'm going to direct to Steven. For a young woman looking forward to her childbearing years, what are current prevention treatment recommendations if she's found to have BRCA1 or 2? And this is important. There still seems to be a large burden on the patient to sort through the risks and benefits. Steven, you have any comments on, what should a 25-year-old woman do and how does she sort it out?
Oh, I think a 25-year-old woman is easy. We wouldn't recommend anything to a 25-year-old that would impair her fertility or recommend anything other than, to enjoy a regular, healthy life at that. I mean, the question is more the 35-year-old. So I think the question could be put as, at what age for a healthy woman do you consider recommending a preventive oophorectomy? And are there options after the oophorectomy which would allow her to preserve fertility? There are, but there are there are a lot of medicine involved. What would be the impact of a 35-year-old woman delaying an oophorectomy till age 40 or 45? Okay, first of all, the mastectomy is relatively easy. If you want to maximize the benefit of a mastectomy, you obviously have to do it at the time before the first chance of getting cancer is. Fortunately for BRCA1 and BRCA2, that's really early, it's 25. I would we recommend it 25, 30, 35. Having said that, it shouldn't really impact on fertility other than breastfeeding, which is an impact, but it's not fertility per se. And there are plenty of women, and I would encourage who want to have babies, don't breastfeed their babies, but that's a separate issue. The big one is oophorectomy. We did find in our study, and we're looking at it continuously, that if you did the oophorectomy at age 35, you had a very close to zero chance of having anything found at the time of the surgery in the tubes, the ovaries or abdomen, or the peritoneal. I would not go earlier than 35. We found in our study the trade-off, if you wait till age 40, you had about a 4% chance of
For
getting
BRCA1,
something.
I just
for
want to be
BRCA1,
specific.
Yeah, right.
Yes.
Right. BRCA2, you could wait till age 45. BRCA1, between the age of 35 and 40, we found 2% of them got ovarian cancer, and another 2.6% of them had ovarian cancer or tubal cancer at the time of pathology. So at 40 years old, you had a 4.6% chance of getting something. Didn't say it would kill them, but they sure as heck all need to be treated. At 35, we found like 1. As a doctor, who does cancer, I gotta go with telling the patient, if you want to minimize your chance of having any ovarian cancer, the age is 35. However,
BRCA1.
for BRCA1. However, if you want to choose to age 40 to preserve fertility, you may not have any kids. I will support that decision, but I have to let you aware of the possible consequences of that delay. That's my opinion. I always say to the patient, the first thing I say is, if you want to get to zero, if you want to get as low as possible, you got to go for the surgery.
So,
You go-
sorry.
If you want to get to something, if you're willing to trade it off, we're willing to discuss it. But, we start with the zero, and then we say, well, everything else, we're open to discussion.
Right, great, and I'm sorry about that. So 2 follow-up questions. One, percentage of women who have their oophorectomy who end up, having a subsequent cancer. Feel free to go low on those numbers, Stephen. There's ranges, so,
Say the question.
So if you said if primary peritoneal cancers and also stick, just the fact that these things are age-related.
So let's talk about primary peritoneal cancer. It is certainly one of the residual questions which is the most vexing. Why? Because if we go back to the breast cancer story, I can say to the woman, if you have breast cancer gene, don't do anything about it. We think your risk of getting breast cancer is up to 70%. If you have a bilateral mastectomy, I'll drop you to 2%, which is way lower than the average woman walking around Philadelphia, which is about 7 or 8%. So I'll take you not to zero, but you'll be better. Don't worry about it. You're way lower than the average woman with breast that doesn't have a mutation. Let's switch to ovarian cancer. We think the range is like 30, 40% for BRCA1 to to age 70. The average woman is 1.4%. 1 in 70 for an average woman, about 1 in 3 for a BRCA1 carrier. If we do the oophorectomy, age 35, we estimate the risk to age 70 to be 6% of peritoneal cancer. Not a disastrously high number, but it's way higher than the 1.4%. You're not out of the woods. We want to get that lower. How do we get it lower?
Address that in a second.
Not sure. Maybe you do it earlier. Maybe you do oral. The two options are this: do it earlier, like 35, give oral contraceptives. Oral contraceptives are very effective in reducing ovarian cancer in BRCA1 carriers. Whether they reduce the risk of peritoneal cancer below the 6% is to be seen.
All right,
Our
so-
study is following them.
Great, thank you. We're just,
Sorry
I
to
have
be-
like, they're all like nudging at me to keep going. So one thing I will say is that 6%, that's one number. There have been other studies that have lower numbers, just so we
Go with the
are
lower.
working on those numbers. One question was the percentage of the time that when you have an oophorectomy, you're found to have an abnormality. And that actually, to answer the question quickly, is age dependent. The younger you are, the lower it is. And this is called a stick lesion, which is a sort of a early form of an ovarian cancer. And it is definitely age dependent. So it's rare in young people, and it's more common in older women. And we're really trying to understand those, also called stick lesions, as understanding the basic early stages of ovarian cancer. Mark, question for you, following up on this young woman: fertility preservation and PGD. You want to make any kind of comments on that?
Well, fertility preservation through self-injectomy?
Well, just fertility preservation, I think that some women are interested in, oocyte harvesting if they're looking at their oophorectomy, things like that.
So there's two theoretical modes of fertility preservation. One that Steven had mentioned in his talk, I think, was the idea of doing salpingectomy, removing the fallopian tubes alone, since we think that many diseases that we call ovarian cancer may actually start in the fallopian tubes. That is still kind of investigational in the sense that we don't have proof that that's a safe approach, but certainly it's a interesting thing to look at for the future. The other issue of doing either oocyte harvesting or alternatively full IVF and storing embryos with or without pre-implantation pre-implantation diagnosis is certainly an option. PGD is usually not covered. And it's expensive, and certainly going through IVF just for the purposes of having PGD is something that's beyond the resources of many people. If you have to have IVF for infertility treatment and then adding on the pre-implantation diagnosis is a little bit less expensive.
But it can always be surprising. Some insurance policies do cover PGD just as is, so it's always important to check your policies. Another question for you, Mark, a question about African American and BRCA1 and 2 mutations, and also sort of concerns about the fact that testing is not getting to everyone, and is that increasing disparities, just access to genetic testing?
Wow. I mean, so African
In
American
30 seconds, yeah.
African Americans and BRCA mutations, yes, definitely. African Americans or women of African ancestry certainly have pathogenic BRCA mutations, and kind of once you move outside of the founder populations, they're probably at about the same rate as an admixed Caucasian. The issue of disparity is something that we were talking about, I guess, indirectly when we were talking about the idea of opening up testing to a broader population. There are issues both with access to genetic counseling resources. There are issues with physician recognition of predisposition in people who are minorities, both Hispanic and African ancestry. There are issues of getting appropriate counseling. There are issues of insurability for testing. There is a problem that needs to be addressed.
So the next one is, do you see PARP inhibitors as first-line treatment in the future for ovarian cancer? And I can tell you that there are ongoing studies right now looking at women who are diagnosed with ovarian cancer, getting their chemotherapy, and then being randomly assigned to get a PARP inhibitor versus a sugar pill to see how that will work. Right now, the current approvals are for after the cancer has come back again. And so these earlier stage studies are making their way through the system. And again, the fact that Roger said Test tubes 2005, first trial 2009, first approval 2014. By 2017, we've got 3 approvals. So we're definitely moving in the right direction. You're going to see more and more coming out about that very soon. I've got questions about ovarian cancer early detection. And, you know, come on, can't we get our act together? It doesn't actually say that, but I'm going to say that. Would anyone like to tackle, well, how are we going to do better about early, ovarian cancer detection? It's a tough one. Steven's got it. Okay.
Well, I mean, the big news last year, I think there was a trial, UKC Talks, which proposed that it could be done. They set up a company, Codia, basically on CA-125. The benefit was very slim. This is for the average risk women. The benefit was slim based on the fact that you had to do it every 6 months, which is a lot for screening. I mean, the current ovarian cancer screening protocols, which seem to work, talk about a 6-month interval. I think that's too often. Colon cancer, which is a wonderful screening test, particularly colonoscopy, they're going as low as every 5 years. I mean, it's pretty amazing. You can do it every 5 years and you can reduce deaths from colon cancer. If you got to go every 6 months, we're, you know, difficult. Like, you can't go for every 3 months. Some people have proposed to do it every day. What that means is they create an app that you stick something and look for circulating cells in your blood. I think that's probably the best way of driving people crazy you could invent. I mean, it goes off in the middle of the night. What do you do? God,
Yeah.
I mean, God, it must be saying that has to be. So then there's been the idea that you can add HE4 to CA-125. I understand has not been a great success. The basic, talking to Karen Liu, who knows this about this well,
She'll be speaking tomorrow.
she will be speaking tomorrow probably about this.
Yeah.
So I would say, I think there's still hope, but we're not there yet.
That's terrific. So, and I've got 3 quick things. Clarify PGD, sorry about that, pre-implantation genetic diagnostics. If someone has a BRCA mutation, she and her partner can go, she or he and their partner can go through in vitro fertilization, screen the embryos, and only have the embryos reimplanted that do not have the BRCA1 or 2 mutation. Some people think it's evil. Some people think it's great. We're the messengers. Technology is available. We're happy to talk about it. But that is a strategy that's out there. Someone wants to know the timeline of the vaccine. We do have a clinical trial in early stage breast cancer patients right now. If it meets its endpoints of immunogenicity and safety, safety is not an issue. We hope within the next year or two to take it into a limited number of BRCA1 and 2 carriers, prove safety and immunogenicity. Then it would require a large randomized trial like Steven's talking about, but you know, we hope that denosumab will be off the ground first. And then finally, funding. How does the Vassar funding help? And I can tell you that in the past, yes, we got grants through the NIH and other organizations, which have been, there are a lot of great organizations out there, Komen, BCRF, et cetera, but to have funding that's specific to BRCA1 and 2, and it is incredibly time consuming to write grants, to submit them, to get them rejected and revise and resubmit. It takes a lot of time and resources. So this mechanism for funding, really, we can't say how useful it's been to all of us. So with that, I'm going to really thank you for your time. I didn't get to all the questions, so for those of you who didn't, feel free to come up and talk to us. Thank you very much.